Hi class, I promise you to give some recorded on interacting spins dealing with Hamiltonian. Look at equation 3.1 here. That is given by two particles. This is particle 1, this is particle 2. Okay, so this particle taking the Hamiltonian is given by multiplications of these two type of particles, where you can rewrite these into this one. Okay, now let's try to look at the initial information that we have. The first thing to look at is what would be the states like. The states would be as, since it's a spin dependent, as spin and also the spin magnetic. Okay, and then you look at the H, operator H, S1 and S2. These operators are all mutually commute. Okay, so that means they share the same states, this one. So if you look at the total two particles, okay, equation 1 here, so your S is equal to S1 plus S2. So if you have 3 particles, what would be like? So your total will be S1 plus S2 plus S3. Now yang considering spin half, both spin half, so you can denote that this one is half. Okay, so you have half ms, and another is also spin half, so your state will also spin half ms1, ms2. Okay, that will be the idea. Remember, we always look at these actions of operator. All right, so s square, and also at one of the directions, these give you the eigenvalue equation. All right, so whenever s square acting on these states, these are their energy. Sz acting on this state, mh bar is their energy. Okay, you need these two to describe the system. In this case, describing two particles. Okay, so if you look at s square, all right, so you just have to add these two particles, s1 plus s2 square. You expand here, and then you expand more, but now look at this particular part. Since they are mutually orthogonal, so your s1, s2, they are commuting. Okay, so it seems that you can treat either, the order is not important, so you have the 2s1 s2, 2s1 times s2. Therefore, you can rewrite this s1 s2 after you do some change. Okay, let's see. So from here, you have h lambda. So you have 1/2 s1 square minus s1 square minus s2 square. Okay, look at equation 2. So next, you're able to compute their energy. Okay, so the energy is what? So what is the possible state possible for S? So S1 minus S2, let me fix this, minus S2. So this will be your possible state, S1 plus S2. So your S will take between this region. So half plus half plus half, plus minus. So you have 0 as 1. So your possible S is 0 and 1. Now you want to compute energy levels. So you have H, this is your states. So you have lambda square minus S1 square minus S2 square acting on the same state. Okay. So lambda square, S square, okay, you can separate them. But to be exact, this is S1, MS1, this is S2, MS2. So what would you produce? You have lambda square. This one acting on that will produce S plus 1. You can take out square H bar minus S1 plus 1 minus S2 plus 1. Okay, and then you have SMS. So by right, you will have lambda H bar square 2 S plus 1. You simply substitute. So you have lambda square over 2 plus 1 minus 3/2. Okay. Then you can have, if F equals to 0, then your H or your E equals to, put it as L0, H bar square 2 minus 3/2. Okay. If S equals to 1, your energy, say put 1, then you have lambda, you substitute 2 minus 3/2. So what do you get? Two, so you have 2 by 2, 4. So you have 1, 4. So that's all. Okay, thank you.